Hello, and warm welcome to Func Prog Sweden number 10. We are back. And warm welcome wherever you are in the world. Today's agenda. The usual one, I'll do an intro, and then we will have a presentation using Rust with Elixir for code reuse and performance by Niklas Begley. And then we have AWS Lambda and Clojure in Anger by Juan Facorro. And in the end, I'll do a schedule and summary. But due to some, believe it or not, technical issues, we'll flip the agenda a bit. So we will start with AWS Lambda and Clojure in Anger by Juan Facorro. So first up, I would like to thank OtherBeat, our video sponsor. OtherBeat is a small IT consultancy company here in Stockholm, where most of the developers have a background or are working with functional programming. If you want to support the community, and of course you want to support the Func Prog Sweden community, you can join the MeetUp community, or you should follow the YouTube channel. And of course, we also have a little fun merch store where you can find mugs and more t-shirts with our logotype on. So check that out also. There's the link below the video. If you have questions during the presentation, please use the YouTube chat and I will interrupt the presenters and read it up to them, or I will take it in the end. With that said, let's get started, and I'll hand over to Juan. Welcome to Func Prog Sweden, Juan.
Thank you. I'm glad to be here.
Yeah, you're warm welcome.
Me.
Yeah, it's really nice. Finally, someone in the studio. We had most people on link for a very long time, so now we're gonna connect and hope that this works.
Let's hope so.
Yeah. So welcome, Sean. Let's see. Oh, it fires up. Yay. So over to your presentation.
Okay. So thank you. Not that. Thank you for joining today. I'm going to talk about AWS Lambda and Clojure in Anger. So first, I would like to make a clarification because I saw a message in LinkedIn. What does it mean to use what the expression in anger means? It means to do or use something in a real situation. It's not so much about the feeling, or even though we all get frustrated sometimes with our code, it's less about that and more about using it in a real situation. So who am I? Less in the existential sense, but like my background. I am Juan Facorro. I came from Argentina 5 years ago to Sweden. I was reached out by Klarna, which is a payments company, or was mostly a payments company at that time. Now it's a full-fledged bank, apart from being a payment company. And the first few years at Klarna, I was doing mostly Erlang, since I was also doing Erlang back in Buenos Aires, Argentina, where I'm from. And I actually worked with Brujo Halcon, which also presented in this meetup back in Buenos Aires. And a year ago, I moved into a team that is using Clojure and Lambda in production. This has been something that I've been wanting to do for a long time, even before I started using Erlang. But then I got into the Erlang world because it's an amazing community and language, and so I ended up now, after some years, with using Clojure in production. So for those of you who are not that familiar with either AWS Lambda or Clojure, I'll give you like a short introduction for each. Clojure is a functional programming language. It's a dialect of Lisp, and it shares with Lisp very characteristic things like the code as data philosophy and a powerful macro system. It's a predominantly functional programming language, and it features a rich set of immutable and persistent data structures that let you manipulate data in an efficient and transparent way. It is compiled. It is a compiled language, but it also provides all its dynamic features at runtime. And it it was designed to be a hosted language, so it runs on many different platforms. The original one, or the first one, was the JVM, but there are other official versions which run on JavaScript or the .NET CLR. There are other unofficial versions that, for example, one that I have built and maintained, which run on the Erlang VM, but that's not the one that we use at Klarna. We use the one that runs on the JVM, the official one. AWS Lambda is an event-driven serverless computing platform that is a service provided by AWS starting from 2014. So it has some years on its back. It has matured along the way. It allows you to run code in response to events, and it also takes care of automatically managing the computer resources that you need to run that code. So you basically find a piece of code that takes an input and produces an output. So you can, it's a very nicely functional model in that way. And since it's an AWS service, it can integrate with all of the other. It integrates very well with all of the other AWS services, like API Gateway, in case you want to build an HTTP API using AWS Lambda, or if you want to consume from queues like Kinesis or SQS, or you can even integrate with data stores or databases like DynamoDB to consume events for creation of records and such. There's also a way of integrating with S3 in case you want to subscribe to events from your S3 buckets, for example. The default runtimes that are provided by AWS are these. The one that is the latest ones that are provided are here, listed here, and Java 11 Corretto is the one that we use at Klarna. This is where Clojure is running on, and Amazon Corretto is a distribution of the Open Java Development Kit, OpenJDK, that is maintained by Amazon and includes performance enhancements and security fixes. So the very simplest Clojure Lambda that I could think of is this one. This is the way that you would write a simple Clojure Lambda that just spits out hello world as the output, no matter what the input is. There is a contract that you need to subscribe to, which is an interface, in this case the request stream handler, and it's a very simple contract. So you can, the boilerplate that you have here is very small, but you can replace this if you don't want to repeat this with libraries that are out there. In our case, we don't feel like this is such a big boilerplate, and we like to be in control of the details. So when I say we, I mean the team that I'm part of at Klarna today, that we use this every day. And what are we using these two things for, Clojure and AWS Lambda? Klarna got the banking license in 2017, and there was a decision of either building a core banking platform, a core banking system, or paying the license for a product that was already a core banking system. Klarna decided to invest in building its own. The team that I'm a part of at Klarna today is part of this core banking system, and it provides its functionality through Clojure running on AWS Lambda. Some of the products, so this is part of the team that I work in, provides the services that are the back end, very deep, of products like the Klarna savings account in Sweden that is in production today, and the Klarna bank account in Germany, which is also in production since this year. In a very abstract way, the service does the following, or what is here in this diagram. It receives asynchronous events, and there's a set of lambdas that process those, and also it emits asynchronous events, and there's another set of lambdas that process those as well. We also have a synchronous API, which is basically an HTTP API that is integrated through API Gateway. And for our asynchronous lambdas, we have encountered no challenges or limitations from using Clojure on the JVM. There is the full support and libraries from both the Clojure and the Java ecosystems, which provides us with all the tools that we need. We have been able to meet all latency requirements for the processing of these messages and events. And Clojure is fast. It can and does perform at the same level as Java in most cases. And it has never been the cause of bottlenecks in our experience for the asynchronous flows. The synchronous case is a little bit different. The JVM is known for providing slow startups, and Clojure on the JVM suffers from this, unfortunately. So luckily, there are multiple workarounds and options to address this. The life cycle of a Lambda is the stages that it goes through whenever the Lambda is not available yet. There is no instances of a Lambda available. It has to be instantiated or initialized. And after it goes through the init phase, initialization phase. Every time that it's invoked, you get an execution of your code. And eventually, if the Lambda is idle for enough time, it will get shut down. The amount of time that it takes for Lambda to get shut down is nowhere specified in the AWS documentation. There are some people that have made some experiments, but there is no official time. It can also happen that a Lambda gets recycled. The instance gets recycled for some reason. These are all internal things in the AWS Lambda service that are not so much exposed to us. But the point is that in the initialization phase is where the JVM startup happens, and all the code is initialized as well. In there, you can see the runtime initialization, the function init, and we will leave out the extension init because we are not concerned with that. It's a specific feature from AWS Lambda provides, but we don't use it. So cold starts are affecting every time affect your HTTP API, for example, every time there are no available instances of your Lambda yet alive, and you have a request that needs to be served. If you have enough load, it can happen that even if you have live Lambdas, you will get one request that cannot be served by your current instances, and then there will be a new instantiation of this Lambda. So what influences a cold start are JVM startups and class loading, for example. The memory that's configured for Lambda also affects how long does it take to initialize. There are some JVM tuning that you can do regarding compiler optimization levels that affect how long does it take for this to spin up. And there's also static initializations that we will go into as well. So for the JVM startup, this graph is meant to communicate that the number of code that you have in your Lambda affects directly and proportionately how much does the JVM take to start. So on the y-axis, we have how much does it take the init phase, how much the init phase takes. And on the x-axis, we have how many functions there are. The three lines of different colors are for different sizes of each of these functions. So it's not surprising what we see here, at least not for the JVM, but not every virtual machine behaves in the same way. And this graph only confirms what we said before, the fact that if you put more code into your artifact for the Lambda, then you will end up paying more, a higher cold start. So the point of this is that you have to be mindful when building a Clojure Lambda, or in any case a Java Lambda, the fact that you should be mindful about the dependencies that you use. It's very common for bringing in one dependency and then bringing in a bunch of other ones. So you might end up having more than one dependency that does the same thing, like HTTP client or JSON parsing. That's not unheard of. And also, you should keep your Lambda lean and functionally limited, in the sense that you shouldn't put a bunch of different things on the same Lambda or the same artifact and then deploy that thing, because that will affect your cold start. The next thing that directly affects the startup time is how much time you have configured for your Lambda. So the service, the AWS Lambda, allocates CPU to each Lambda proportional to the amount of memory provisioned. So you can have access of up to 6 virtual CPUs when the memory is configured to 10,240, which is basically to 10 gigs, but it is expressed when you configure it in megabytes. The pricing model for AWS Lambda is that when you execute the function, then you get charged by each millisecond of execution, and based on the memory that you choose, you will get charged proportionally to the memory for each millisecond. As we can see in this graph, which is showing the init duration based on the memory, and these are all measures that are not extremely scientific, because it's one sample from running the very simple Lambda that I showed before, but it's the bare minimum that you can get without doing anything else. So this is showing that after around 4 gigs, you don't get that. There are diminishing returns in increasing the memory, at least for cold starts. I mean, you can also get more CPUs and increase the memory for other purposes if your Lambda is doing like heavy computations. But we're talking about specifically, in this case, about synchronous Lambdas that are used for synchronous communication that shouldn't pay for cold starts, or it's inconvenient for them to have a high cold start time. So the third point here is tiered compilation. So a way to minimize the time taken to create a new managed execution environment is to tune the JVM. And a managed execution in this case is just spinning up the instance of the Lambda with the JVM. The way that you do this is that you provide an argument to the JVM so that it doesn't do all of the levels of compilation that it by default does. There you can see in the slide that by default the JVM does all of these levels, but you can which includes profiling and full profiling, and then optimization on that native code that gets both profile and compiled. So you can limit this into level 1, and it also depends on how does it affect your workload. It depends on what kind of work you're doing. If you have an HTTP API and you're just mangling data, it won't affect that much. If you're calculating hashes, if you're doing hash calculations, it will probably will, because you will have a very computing heavy piece of code that iterates a lot. So that benefits a lot from optimizations. But for example, in our case, setting the level to 1 doesn't really affect our latencies. For example, our 99% percentile latencies. But you should always measure. And this is one of the things that you can do as well. That graph shows how does with and without affect based on the memory chosen for the same Lambda. Here we can see that at 3 gigs with compilation, we are under 1 second of cold starts. The last thing that I wanted to mention of the list that I showed before are static initializations, which is on the JVM, and because Clojure is compiled on the JVM, you have static constructors and static initialization blocks, which that's code that gets executed when a class is loaded. And some of these are necessary. For example, when you want to initialize clients for HTTP, or when you want to load environment configuration only once, or thread pool creation. In Clojure, the top level expressions are generally put in a static initialization block, and sometimes you cannot avoid this. You could move this away from this block, but then you would have to pay, instead of only once when you load a class, you will have to pay this for every single invocation of the Lambda, which is not a good trade-off anyway. So the alternative to this, so if you find that reducing all of these cold starts, it ends up not allowing you to reach the cold start or the level of latency that you want for the first invocation of each Lambda, and you must absolutely do better, there is an alternative that is keeping your Lambdas warm. So when AWS Lambda was released on 2014, the way of doing this was a bunch of manual workarounds, and this existed for many years. You just have to Google like keeping Lambda warms, and you will find the approaches that people, if you go back some years, you will find the approaches that people had. But in 2019, the service released a way of configuring your Lambda called provision concurrency, in which you can ensure the number of instances that are already available. And you can, if you have predictable load, this is a very easy way of saying, I want, at this point of time, I would like this amount of Lambdas available, and then you can play with that as much as you want. If your cold starts are quite high and you have quite steep peaks, then it gets a little bit more complicated, because if you have high cold starts, then applying auto-scaling based on the load might not react as fast as you need. So this is a solution, but it's a limited solution based on your load pattern, basically. It also has specific pricing, and it comes with, which means an extra cost. And you can check out what that is. That's also another factor that comes into play when you choose to do this or not. So there are some general limitations and caveats that I would like to mention for AWS Lambda, and the way that we found that we've used it, sometimes in the wrong way. So there is a maximum execution time. This is in the documentation. So this is the maximum time that an invocation can take. And this is not an issue in general, because 15 minutes is a long time, but it's something to be aware of. But because, for example, it is not a good idea to use a Lambda to perform jobs for which that take a lot of time, and then the time that it takes depends on some other factor, and that factor keeps growing, like, for example, the amount of records in a table, or the amount of data that you have in a bucket, or something like that, because eventually you will have to address that, and that's just a ticking time bomb. The second thing is related to the init phase that we saw in the life cycle of the Lambda. The first one has a timeout of 10 seconds. If your Lambda has a cold start of more than 10 seconds, then it times out in that phase, and it repeats all of the work on the first invocation of the Lambda. So you end up paying double, basically, the cost of the init phase if it takes more than 10 seconds. This is in the documentation as well, but it's extremely easy to miss, in my experience at least. So, and the last caveat is that provision concurrency. When you update the version of your Lambda, there is a mechanism through which you have an alias, so like a named version for your Lambda, and then you point a version to that alias, and then you change that version, and all of this is automatically done by the AWS service. It's just a feature. The thing is that there is a non-zero chance that if your system is under load, when you do this, there might be some of the invocations that will pay the cold start because they cannot be resolved to one of the two versions of provision concurrency that are migrating from one to the other. This is something that we've like a confirmation that we've gotten from the AWS Lambda team, and it's because of the way that the change is being orchestrated in the background. So the alternative to this is to hand roll the migration of the traffic from one version to the other. If you find that you cannot pay you cannot take the risk of some of the invocations to pay the cost of the cold start. There are some things that we haven't discussed, which is alternative platforms that have a lower startup time, like using ClojureScript, for example. Before I joined my current team, there were some experiments using ClojureScript. The feedback that I got was that the tooling at the time was not on par with the tooling on Clojure on the JVM, and they found some issues, so they decided not to go for ClojureScript because we could find alternatives to address the cold starts and the issues that we would not have had with ClojureScript. The second thing is is using GraalVM. So GraalVM is a Java VM implemented in Java. It supports a way of doing ahead of time compilation for Java. This means it compiles Java bytecode into native compilation, into native code, sorry, and this translates into lower memory footprint and also faster startup times. And the first production-ready version of GraalVM was released on May 2019. We have not explored. We have explored very superficially how would that work in our case, but we have still to explore it further. But this is a good option for those of you who would really like to get the cold starts to the bare minimum, because you would be able to run native code. There are other there's a different setup that needs to happen, and that is work on its own, but it's an option. And the third thing that we haven't discussed, which is also an option, is that there are ways of defining and using your own runtime when using a Lambda function. For example, if you want to use a different JVM distribution than the one that is provided by default by AWS. And there's a lot of options in that space that we, again, haven't explored. But there are even libraries in the Clojure world which allow you to, that they define the custom Lambda runtimes by themselves, and then you can build on top of that. One of them is called Holy Lambda, and we have, again, very superficially explore that one. So some closing words. At the risk of falling into the trap of confirmation bias, because we've chosen this technology and we're happy with it, and we're like further down the path since we started, we have found that Clojure is not only a great language for fast prototyping and creating MVPs and exploring ideas. It is also great for bringing ideas into production and evolving them. When using on the JVM, it is very well suited for handling asynchronous flows with AWS Lambda. But because of the high cold starts in a synchronous API case, it requires a lot more considerations to assess if it's suitable for your specific traffic patterns and use cases. We found that provision concurrency is the right tool for us for our current needs, for example. Since its conception and prototyping, the evolution of the system that I am part of, my team is part of today, was such that separating functionalities in Lambda functions and artifacts allowed us to clear separation between components, which enabled new form teams to take ownership of existing functionality and maybe decide after what to do with that. There have been some functions that were done in Clojure, Lambda functions that were done in Clojure, and then the team that took them migrated to something else because it made sense for us, for them. This sounds like the natural path for a growing system, but I think the fact that we were using AWS Lambda allowed each team to decide this a lot more separately. Once they were fully spawned and the responsibilities were set. And most often than not, there are multiple reasons for a specific result. The team I'm a part of is quite small and very productive, and this is because our team is formed by very capable and awesome people. But I also think that Clojure is another key factor in this situation and in this result. And finally, I would like to say that we are welcome people to reach out because we are looking for all kinds of engineers, and especially if you're interested in Clojure and building a bank, you can reach out to me. So, any questions?
First up, thank you very much for your presentation.
Thank you.
Very good presentation. I will start shooting directly. Do you need to know Clojure before joining Klarna?
No, not at all. If you're willing to learn, we don't expect people to know any particular language. We expect them to be curious and be willing to learn, basically. So
sounds good.
Yep.
So if you're interested, you know where to find it. We had one question during the presentation around the startup time. It was like class data sharing. Will it help to improve the startup time?
Yeah, so that is already, we try that, but that doesn't affect it. But what I believe is because that is already included in the runtime that Amazon provides. So it doesn't in our case, at least.
Okay. Yeah. Then you made the transition from Erlang to Clojure.
Yes.
Was it hard?
No, because I started Clojure. I started with Clojure before I started with Erlang.
Oh.
So I basically ended.
It was the other way around, maybe.
Yeah. So I was looking for a job in Clojure in Buenos Aires, and then I went to a meetup, an Erlang meetup at Inaca, and it was a functional language. It sounded very interested. I met some of the people there, not very in the meetup, not very deeply. And I reached out to El Brujo, Alcon, and then they were looking for people, and then I mean,
so that's the way.
The rest is like 7 years after, I'm working with Clojure.
Okay, don't walk into an Erlang meetup; you might end up coding Erlang.
Yeah, exactly. Yeah.
What would you say? There's a lot of similarities between the languages, or it's like you learn one function, you learn to think functional, and then you can just learn the semantics of the different language?
I think the functional way of thinking, I think it is very similar. I think Erlang is quite data-oriented as well. It doesn't provide as much support, or in my opinion, as much nice support for manipulating data structures as Clojure does, because Clojure brings all these abstractions over data that allow you to use the same function for multiple types of things, and the composing, it's much more concise, and that's why I think ends up being more powerful in my opinion. But Erlang, the way of thinking about systems in Erlang and decomposing the problems, I think that is very similar between the two languages. But I think that's also part of functional programming in general.
Yeah. Okay, let's see. No more question. We have a thank you for your presentation, and again, thank you very much.
Thank you.
Very good very interesting presentation. Thank you very much again.
Thanks.
And thanks for coming.
Thank you for
to us at Func Prog Sweden. Yes. Then we will go over to the next presenter, Niklas Begley, using Rust with Elixir for code reuse and performance. Welcome, Niklas. I know it's late where you are. Yes. I hope you. I hope your laptop will survive.
I hope so too. Yeah, and the power of caffeine compels me.
Yeah, exactly. So let's kick it off. And again, welcome to the Func Prog Sweden.
Yeah, thanks very much. Yeah, so I'm here today to talk about, using Rust and Elixir, and how we use those two languages for both code reuse and performance. And this is going to be kind of a story style talk. So it's I'm going to walk through the scenario that I found myself in as I was building Doctave, and I had these technical problems that I had to solve. And kind of unexpectedly, I ended up finding that the best way to solve this problem, or this set of problems, was actually by combining these two languages in a way I hadn't done before. And I'm hoping you're going to find it interesting as well. So a little bit more about myself. So my name is Nick, and I'm a founder of a company called Doctave. I'm a software engineer by training, based in Helsinki, but currently on the road. And yeah, I worked mostly in kind of early stage startups during my career. Right now, I am working on a new company called Doctave, and this is a Docs as code solution. So for all your developer documentation needs, the idea is that you can store your Markdown documentation in Git, and you push your changes to your documentation to us as part of CI/CD, and you get this nice place where you can read and search all your docs in one place, but still get all the benefits and the developer ergonomics of using docs as code. So you can do documentation reviews and pull requests and so on and so forth, and use your favorite editor to edit Markdown. Yeah, we're founded in 2021, and we're currently in open beta. But yeah, so I'm going to talk into a little bit of background about how I came about, how these problems that I had to solve came about, and then how I went about solving them. So Doctave comes in two parts. So the first part was actually, it started its life as an open source project, and still is an open source project today. It's a static site generator, which is built in Rust. It's open source, free to use, and it takes your Markdown files and it'll build a very nice, easy to use developer documentation site from them. And you can deploy those sites on your favorite static site host of choice, whether it's GitHub Pages or something else. And then we have also doctave.com, which is the paid service that we provide. It's built in Elixir, and more specifically the Phoenix stack. And you can think of it as a specialized hosting platform for Doctave documentation sites. The idea being that if you just have one project that you want to document, the open source solution is fine. But if you have n different projects, you might want to have them all under one roof. And yeah, so the Rust CLI came out about a year ago, and I chose Rust for it, partly for speed, but I think actually more importantly than that, I wanted this CLI to be as easy as possible to distribute. I previously worked at a company that had a developer toolchain that was built in Ruby, and that was just a nightmare to get working on developers' laptops, especially if they weren't Ruby developers and didn't have a proper environment set up. So the power of Rust and also languages like Go and Zig and so on and so forth, is that you can compile them down to these nice static binaries that you can just drop in your path, and they work, out of the box, very, very easy to use. So that was the main reason for using Rust. Also, I'm a big fan of the language in general. But of course, Rust is probably not the best solution if you want to build a web application. Some people are doing that, but they're very brave people, kind of at the cutting edge of technology. So instead, I chose the Elixir and Phoenix for the web platform for us. And the Phoenix stack I found is incredibly you can be incredibly productive in it as a web framework. You get these features that basically no other web framework, gives you out of the box. Like, I'm not going to go into them in detail now, but I encourage you to go and look at the feature set, and things like live view and built-in distributed pub sub and presence systems, and of course, Elixir being built on the Erlang platform, you also get all the benefits of OTP and Beam, built in. I'm going to talk about that in a moment as well. So one of the goals here, of course, was that the HTML that we generate, had to be identical, both when we were using CLI and Doctave.com. I didn't want them to be different. But of course, now these two things are built in two different languages, so this presents itself with a problem. Like, how are we going to actually make sure that we achieve this goal? And because this is kind of a key feature of Doctave, we need to do this very well. So on the Rust side, what we were doing, we pulled in a library called pull-down-CMark, which is a fantastic library for dealing with Markdown. It adheres to the CommonMark spec. It's very fast, and it's also very versatile. You can actually do some very cool customizations with it, where you can augment the AST as you're parsing it. Very, very powerful. And on the Elixir side, then when the time came to actually start building the Elixir side, I pulled in the main Elixir Markdown processor, which is called Earmark, made by the famous Dave Thomas, and I put this in and I sort of called it a day. But of course, there's a few problems here. So one of them is that Markdown, when I say Markdown, usually people understand what we're talking about, but it turns out that Markdown is not very well standardized. There are a few quote unquote competing standards of Markdown, and there's not necessarily any guarantees that two different Markdown libraries are going to produce the same output for a given input. There might be different features that they support, or there just might be subtle differences that creep in. And also, like I mentioned, we were, the Rust to Markdown parser, gives us the ability to customize the output, and we're actually using that for a few things in Doctave. So you can, for example, Merbe.js diagrams. You can embed charts into your Markdown files. Also things like callouts, where you can kind of highlight a piece of text or piece of content if you want to bring attention to it on the screen. And kind of smaller things like being able to use emoji shortcodes, kind of like on GitHub, and get those rendered out, in the browser. These are problems that they weren't immediately at least solved, by using these two libraries. But I was at this point I was busy building Doctave.com, and I had a million other things on my to-do list and of things I had to build. So I decided I'd deal with that later. So fast forward a few weeks, and I realized that actually some of the requests on that we were doing were taking a suspiciously long amount of time. And I kind of started digging in, on Doctave.com, and I started digging into what was going on. And I realized that actually Elixir was spending a non-trivial amount of time parsing Markdown. So if you usually kind of the way we think about this is that web request budget, tends to be about 100 and 200 milliseconds, depending on, depending on who you ask. But that's kind of that's the budget that you have if you want to have an application that feels snappy, so to speak. So as you can see, so in this chart, you can see that this has inputs of between 2.5 to about 160 kilobytes. And what you can see is that, as we start having bigger and bigger inputs into the Markdown inputs into the Elixir Markdown processor, we actually start taking like on the order of hundreds of milliseconds fairly quickly. And if we want to actually have a performant website, we can't really be spending 400 milliseconds just parsing this Markdown. This seems very, very wasteful, and we wanted to do better. So of course, what's the solution that any self-respecting software engineer would do to solve this? We build a cache, of course. And this is where, Elixir and the Erlang ecosystem, of course, shine. I'm going to walk you through like how we actually ended up solving this first. So since this is a functional programming meetup, I'm going to assume that most people are fairly familiar with Erlang, but I'm just going to give a whirlwind tour of the basics. So Erlang, of course, is famous for its actor model, and the idea of having massive concurrency, being able to schedule these lightweight processes, up in the millions if need be, with very small memory footprint, and they can be kind of terminated and created at will. And your program ends up looking like a tree of these processes, like these the processes are further up in the tree, supervising the ones at the bottom, making sure that if they fail, they get restarted, or and so on and so forth. And this is kind of where Erlang gets its fault tolerance and resilience. Well, that's why it's famous for it. But another thing that's also built into Erlang is something called ETS, or Erlang Term Storage, which is the simple way of saying it is that it's an in-memory key value store, or you could even call it a database because it has some fairly interesting query functionality as well. But yeah, you can actually you don't have to pull Redis or Memcached or something like this into your stack if you're using a system on the Erlang running on the Beam. you actually already have these capabilities built into the language. So the solution that we ended up building here was that kind of looks like this. So the idea is that if a web request would come in, we would hit a renderer, which would then talk to a process registry, which supervises a whole bunch of processes that are responsible for a given project's markdown in HTML. So the renderer would ask, hey, can you give me the ID of the process that owns this particular piece of content? The process registry will respond and say, hey, you need to go talk to this guy. The renderer then goes, hey, can you please give me the rendered HTML for this given input? And the project process now, if this is the first time it's being asked this question, it's going to generate the HTML, by calling earmark, and cache that HTML in ETS, and then send back the response. And if this is the second time, or that it's seeing that, it's just going to go straight to ETS and return the HTML. And this is a fairly like simple but functional cache. And a really cool thing also about Elixir and Erlang in general is that what you can do is you can tie the lifetimes of these project processes to the ETS table entries. So what you can do is that these project processes, you can say that, hey, I want you to terminate yourself if you don't actually get any traffic within 5 minutes. And then when you terminate yourself, when you do that, clear the ETS entries that you're responsible for. So this is where, so you can actually get this kind of dynamic clearing of the cache, for, cold projects that are not being accessed at any given time. Now this is what we actually went with for a little while, and it worked decently. But of course, is there a better way? The problem with caching is that you solve one problem, but you introduce like 16 other ones. What happens if you have a ton of traffic that comes in? You could start running into memory pressure, and caching is just a difficult problem overall. And while we did solve the performance problem here, we did not solve the standardization or the feature parity problem that I mentioned earlier. So we still have that to attend to. So I started looking around for a different way to solve this completely. And that's when I came across a fantastic project called Rustler. So Rustler is a library for writing Erlang NIFs in Rust. So Erlang NIFs stand for native implemented functions. And the idea is that you can include some native code as part of your runtime in your application. And then your Elixir code can invoke those native functions as if they were Elixir functions. So of course, some functions in the Beam or in the Erlang VM are already written, in C, and they're compiled into native code, and you can invoke those. But in a similar way, Rustler allows you to inject your own library code into the runtime. And Rust is actually a really good choice, arguably, for writing NIFs. NIFs are sort of dangerous in the Erlang world, because if your NIF crashes at any given point, it's actually going to bring down the whole Beam process. It's not. It's all the fault tolerance guarantees that Erlang has just go straight out the door. The whole operating system process will come crashing down. So you need to be sure that your NIFs don't crash. And this is why Rust's compile time guarantees, where they come in, where they really shine. Rust, it's a low-level language, but the compiler and the type system provide these memory safety guarantees and concurrency guarantees also, that really kind of completely eliminate a set of bugs, assuming you're using safe Rust. And you can sort of just kind of rest assured that, at least compared to writing a NIF in C, this is going to be a lot safer. So yeah, so I looked into this, and this seemed like a really, really good option. So, what would it take to actually put this in? Well, the first thing I did was actually I took the Markdown rendering portion of the CLI that we had in Rust, and I extracted it into a Rust crate. So that's actually, you can actually go and see it on GitHub as well if you like, and it encapsulates the logic for parsing a Markdown document into HTML. And essentially, it exposes like a single function called parse, and you can pass into it a string and an optional like a configuration struct that will set certain parameters on it. And I'm actually going to show some screenshots of some code now, so just to show how easy it was then to pull this in. So what Rustler will do is Rustler will create a tiny little embedded Rust project inside your Elixir project. And in there, what you have to do is write the glue code that maps the Rust data structures, to the Elixir data structures. Excuse me. So what you see here is that parse function. At the top on line 16, you can see this is a Rust macro. It's basically just saying, hey, Rustler, expose this parse function for me. And all the function is doing is taking those arguments from the Elixir side, converting them into the Rust specific ones, and then on line 37 we're just calling that Doctave Markdown parse function with the given input and the options, and returning a data structure that Elixir can understand. And that is pretty. That there's another maybe 50 lines or 30 lines that I've omitted here just for brevity. But like the whole glue code is less than 100 lines in this case. On the Elixir side, this is the whole parser module that where the Elixir parse function here will then on runtime get replaced by Rustler with the function that I just showed on the other side. And this actually turned out brilliantly. So what we ended up doing was we went from this, which is not super complicated, but it's not trivial either, to this. Now the renderer just calls the Doctave Markdown library, and it gets some HTML back, and it's a lot faster. So with Rust, it turns out that we rarely spend more than a single-digit millisecond rendering Markdown, and which is not very surprising. Like Elixir is a very fast language when it comes to like kind of massive concurrency and like an IO, but for CPU bound tasks, it's never going to be able to compete with something like Rust, which compiles down to native code. So I thought this was a huge win, because essentially, this caching, with this caching solution, we were trying to kind of solve this problem of it taking too long, but we still hadn't, solved those other problems of, code reuse and having to re-implement things twice, and maybe having issues with the output not being the same. But I felt that like this Rustler solution really just made the problem go away completely. Now suddenly we can use the same code in the same place, like in two different places, and we also made things a lot faster and a lot simpler. The integration that Rustler lets you do was extremely straightforward. It was an afternoon of work, and this was just a great win. And now we're 100 times, and we're also 100 times faster, and things are simpler. So what can we actually learn from this? Like I just said, cross-language integration, in this case especially, was delightfully simple. And it can sound scary sometimes, how are we going to make these two languages integrate with each other? Is it going to be really complicated? But at least in this particular case, and I can't comment on other language combinations as much, but this actually I felt like was a huge win. And I think a big shout out has to go to the Rustler maintainers, who really made this whole process incredibly easy. Of course, there are some caveats here. So, this will mean that, when you're developing the Elixir code, you're also going to have the Rust toolchain installed. This is going to have implications for CI/CD. The Erlang NIFs, of course, have those gotchas that, I mentioned earlier, and plus some other ones that you need to be aware of. Yes?
I just jump in, and we got a question here. Like, can you speak a little to the architecture you have on running this on?
Are we talking about the actual hardware or?
Good question. I don't know. It says architecture.
Okay. I see. Yeah. So at least, I'll talk about how we deploy this in production these days. So we're using a hosting provider called render.com for Doctave, and the way this gets deployed in CI/CD is that we have it's everything's put into Docker. So we have when we do a production build, we'll have a builder image that pulls the Elixir and the Rust tool chains in, does a build, creates what's called an Elixir release or a mix release, which is essentially a self-contained package that has the Erlang runtime, and the Elixir runtime, and also whatever your own code is. And so you don't actually have to have any. You basically don't have to have any dependencies installed on the system where you deploy this system on, assuming, of course, you're running on the same CPU architecture, and so on and so forth. And then once we have that image, we pull that into sorry, once we have that package, we pull that into a different Docker image, which is a very lightweight kind of production runtime image, where you just dump that mixed release, and that will contain the natively compiled Rust code as well. So it all gets put into well, Docker manages this all for me, and then finally at the end of the day, we publish a Docker image to production.
Thanks. Please go on.
Yeah, if I misunderstood architecture here, do let me know. But yeah, so and of course, so where was I? Yeah. So you also want to kind of be wary of the strengths and weaknesses of your language. Rust. I'm a big fan of I'm a big fan of Rust as a language. I would never want to write a web application for it unless it was experimental or performance was absolutely critical with it. Elixir and Phoenix allows us to be way more productive. But in this particular case, Elixir just wasn't fast enough for us to actually write the simple code, and Rust let us write the simple code. So this is just something to keep in mind. And this code reuse was pretty interesting. Like we of course say don't repeat yourself, and I don't want to kind of start a trend here. I don't necessarily want to kind of be a hashtag thought leader in any sense, but perhaps actually there are other cases where like languages like Rust or Zig or C++ or maybe where it could be used with your other language right now in these performance intensive parts, or in cases where you really want to be as fast as possible. And maybe it actually isn't that hard to integrate these languages together. Crazy example of that, of course, is that you have these with web applications, especially you have this front end, back end logic, a divide. We have WebAssembly now. Maybe there's actually ways we can share code, written in some kind of lower level language, and then pull them into other environments. I think this requires a bit more work, but I think this particular case was definitely an interesting exercise in that. And I think this is something that I've sort of been talking about as well, and kind of really relying on, I always want to be simplifying my stack as much as possible. This problem could have been solved in Elixir, just using Elixir, but it would have been more complicated. But then again, one of the reasons we use Elixir already is that Elixir simplifies our stack. Elixir, we don't have to pull in, like for example, Redis or Memcached when we have to reach for a caching system, for a pub subsystem, these sorts of things. Elixir already has got our back, and it just removes another dependency that we have to worry about. And I felt like this, again, surprisingly enough, even though using these two different languages together sounded scary, it actually did simplify things in the end. And of course, there's always trade-offs. It's not a free lunch, but in this particular case, the wins absolutely outweigh the drawbacks. And with that, I'm gonna finish up. So. That's all, and thanks for listening.
Thank you very much, Niklas, for your presentation.
Thank you.
You get applause here from the studio. Thanks. I have one question. How come you started Doctave? What was your motive? You needed to document your own code, or?
Yeah, this is a programmer scratching their own itch for sure. Yeah, I had experiences in previous companies, trying to document my work in general. And, I think a lot of engineers have probably found themselves in a new company and going into the wiki, whether it's Confluence or some other system, and just realizing that everything is completely out of date. And, sometimes the information there is actively harmful. And it turns out that actually a lot of companies that, Google and Twitter and Spotify, for example, they've built these sort of docs as code systems for their engineers to use. And they found that engineers will document code more if you actually let them use the tools that they want to use already. So whether they want to use their favorite editor, Markdown is a simple system. They don't want to use a WYSIWYG editor. And I definitely had felt that, pretty strongly myself. And I wanted this tool to exist. So I've made it exist.
Cool. Also cool that you've shown how easy the nifs are in Erlang. Not that complicated.
Yeah, I gotta say, like, if Rustler didn't exist, I would have had to go and dig into the Erlang documentation. I think it would have been a lot more complicated. I really big hats off to the Rustler folks for making a really solid, easy to use package.
Yes, again, I'm checking if there's no more questions right now. Then thank you very much, Niklas, for joining us and for your
Thanks for having me.
Yeah, you're welcome.
Thank you.
You're welcome. Yes, and with that, then I'm going to summarize today. We'll be back again with the last meetup of the year in the beginning of December. The plan is to have a mixed meetup, meaning we'll actually meet. We'll have some live people in the location in central Stockholm, and as always, we'll stream to everyone else that's not able to join or don't want to join or want to view it online instead. And as always, if you want to present at the meetup, please reach out to me or anyone else of the organizers. We are accepting anyone coming and presenting. You can be the star, you can be the first time presentation. Please come and present. And if you want to sponsor a meetup, just reach out to me. And as always, feel free to contact me on LinkedIn, Twitter, social media, or email, wherever you find the easiest way to contact me. Please just do it. With that said, thanks for joining tonight, and hope to see you all back in December for the last meetup. Bye.